So good afternoon. My name's Alan Smith. I work for a company called Active Solution based in Stockholm, Sweden. And I'm going to be dropping the base with embeddings and vectors in Azure AI Search. What I'm going to be talking about is focusing quite a bit on vector theory. So it doesn't matter if you're using Azure AI Search or if you use something else like Pinecone or Cosmos DB, MySQL, Spotify, and all. There's plenty of other vector search engines that we can use. And I'll be looking at working with text embedding, image embedding, face embedding, and then moving on to looking at music embedding and focusing on how I'm using this in a personal project to find matching tracks for DJ sets. Depending on what comes up in the search engine, there can be, I have had some explicit lyrics coming out. I apologize in advance if anything like that does happen. There will be mathematical content as well, so if that's not your thing, please feel free to move. A bit about myself: I've been writing code for 30 years. I've been traveling around and standing on stages at conferences and involved with the community for about 20 years. I've been in the Microsoft MVP program for 20 years, starting out with something called BizTalk Server, which is just reaching its retirement. Currently, I'm an AI Foundry MVP, so I focus on the machine learning technologies. I do quite a bit with the community. I've organized conferences, helped with the global boot camps, and also Coder Dojos, teaching kids between 7 and 17 a bit about writing code. Very occasionally, I'll publish something on YouTube, so you can check that out there. And best way, if you've got any questions after the session, just feel free to message me on LinkedIn. I'm fairly easy to find. So I got into working with vectors and embedding, with image embedding. And we were working on a project for an auction house in Stockholm. And they aggregate together lots of auction lots from different auction sites. And what they wanted to do is to take the image from these auction lots and put the lot in an appropriate category based on the actual image. So this photo of an E-type Jag would be classified as vehicles. The project was pretty successful. We did have, a few side effects like toy cars would also be classified as vehicles. So we did start to look at doing text classification, but it was a standard problem in computer vision of doing image classification. We used Azure machine learning for it, and fairly successful project. Whilst I was working on that project, I stumbled across this YouTube video. It popped up on my YouTube feed. Eric Bernhardsen, talking about technology that he'd developed for Spotify, which he'd given the name of Spotify Annoy. It's the world's coolest acronym. I'll get to that later on. But it was really this slide that captured my imagination. And what he did was he took a huge data set of images of plates of food. And he says, using vector search, you can find similar images. So the images down the left-hand side, this is what we search for. And then for each corresponding search, we've got the results. And you can see that we're getting similar pictures coming up here. And I thought, wow, this is fantastic. And I was currently working on the auction project. I thought, well, we can take this and we can bang it in the auction site. So when you're looking at a particular auction lot, we've already trained a model to understand the features in those images. We can modify that model slightly, and we can build a similar auction lot site. So when you're looking at an auction lot, it will recommend things that look like the item that you're looking at, where the photos are similar. It worked really, really well in prototype. However, we never got it into production because we were using Spotify Annoy, and it was a bit clunky to get that deployed and running as an API. I mentioned it, I don't know if it's the world coolest, it's my favorite acronym. It stands for Approximate Nearest Neighbor, oh yeah. And Approximate Nearest Neighbor is the algorithms we use when we're working with vector search. The maths is pretty complex, but what we want to find is something that's approximately close to what we're searching for in high dimensional space. So Annoy is free. I still use it. Very easy, like 10 or 15 lines of Python, you can get up and running with it. And it's quick and it runs on premise, and you don't have to give a bag of money to a cloud provider to run it. So you can download that from GitHub if you want to do that. So a bit about vector theory. We work with something called an embedding model. And basically, what an embedding model is going to do is it's going to take data items, and it's going to convert them into an array of floating point numbers. Now, we refer to this as being a high dimensional vector. And the vector that you get out, the dimensions in that vector, will depend on the embedding model that you are using. You may have heard if you're working with large language models and you're building a retrieval augmented generation solution and you're doing search, you will be using text embedding to find similar items in the search as to what people are typing, and that's typically when people talk about that. But as well as text, we can work with image embedding by using an image model. We can work with text embedding and get items out like that. Also with face embedding, we do two things here with computer vision. The first thing we do is face detection, and that's to detect the area of an image that includes the face, and then we pass that off and we can embed the faces to get the face embedding, and this is how face recognition system works. We can also do it with music. We can take a model, and there's various ways that you can embed the music, and then you can find similar sounding music, which all of these I'll be demoing at later on. Now, notice that all of these are really, really high dimensions, and the human brain, we can't really think in anything more than three. Some clever people can think in 4 dimensions. So we can, if we draw that down to 3 dimensions, we all know the red, green, blue color space. We can basically say, well, the color Azure 0, 127255, that's in floating point numbers 0, 0.51, and that's a vector in 3D space. And we can basically put a number of different colors into 3D space, and we can kind of visualize. And you can see that the colors are grouped together with similar colors in similar locations. Now, there's different ways of determining similarity when we're working with vectors. 2 of the most common are Euclidean and cosine similarity. Cosine similarity, we're comparing the angles between those. I don't know if that dark Azure is appearing on the actual screen. It seems to be quite obscured there, but the dark Azure color is basically along the same line. And if you remember back at school, the cosine of an angle of 0 degrees is 1.0. So, according to cosine similarity, Azure and dark Azure and anything that's along that line that's another shade of Azure, they're completely similar. They have a similarity, cosine similarity of 1.0. Euclidean similarity, that's a bit clearer to see, is measuring and using Pythagoras to measure the distance in 3D space or 2D space or 512-dimensional space, depending on what vectoring you're using. So you can calculate the cosine similarity, the cosine between the angles there, and you can calculate the Euclidean similarity using Pythagoras. Now, depending on what you're searching for and how your data is embedding, you may find that one version works better than the other. It tends to be traditional to use cosine first, and there's also a dot product, and you can experiment with different embedding mechanisms. Now, when it gets on to high-dimensional embedding, there's a number of ways that we can use to visualize that, and the best tool I've found is something called Embeddings Projector. And this was developed by engineers at Google along with the TensorFlow machine learning library. And what I've got in here, if I zoom in on this a bit, zoom in on the site a bit, is the data set that I'm using here is called Word2Vec 10K. And it's basically 10,000 words. And what they've done is they've computed the embeddings on these 10,000 words to 200 dimensions. So each of those 10,000 words has these 200 floating point values. Now, using various unsupervised machine learning algorithms, such as this UMAP, what we can do is we can find the nearest neighbors, and we can convert that 200-dimensional space into 3-dimensional space so that we can visualize it, and the human brain can basically wrap its head around where those points lie. Now, once we've done that, we should find, it's going through its epochs, almost there, yeah. What we should find is we get these clusters developing, and if we zoom in onto one of these clusters and highlight the words, you can see there we've got 16, 17, 80, and these are all numbers. Down here we've got voiceless, vowel, consonants, orthography, voiced, and various things. These seem to be related to speaking and language. Over here, branch, rings, norm, coordinate. These seem to be mathematical. Oh, we've even got vectors appearing here. Algebra, Mandelbrot, conjuncture, and various things like that. So those are kind of all related to mathematics. Now, if you study, I do another session called Inside GPT, deep diving into how language models work. If you work with language models, you probably come across tokens, and in a large language model, there is a vector or a matrix, which is known as the token embedding table. All of the tokens have embedding vectors, and the tokens will have similarity, like big and large and enormous will mean similar things. And that's how the maths inside these language models is able to understand the text and be able to make the predictions and generate text for us. But it's not only with, I mentioned, with word embeddings. This is image embeddings. And what I've got is 6,539 photos of dogs. And I've fed those through an image embedding model, and it's given us embeddings of 512 dimensions. Now, I'm going to do T-SNE, slightly different to the UMAP. And what this is going to do is to find similar-looking dogs and group these similar-looking dogs together in three-dimensional space for us. So this is a bit cooler in that you get these dogs being animated and whizzing round, and they seem to kind of get drawn out into a big long line, and then they sort of start emerging into these various clusters. So what have we run? 200 iterations. I'm just going to stop this one now. And what we should see is that we get similar looking dogs grouped in this similar looking space here. You can see that all of these dogs are basically grouped together. And if we whiz around to another area, you can see that these are. I'm also putting on the prediction that the vision model is basically dropping onto that. This is basically what the vision model is saying that this photo contains. An interesting side effect of this is all of these images here. There's a chain link fence appearing in the actual photo, and that is appearing as such a strong feature for the model that it's basically placing all of those as being similar items. Sometimes you get ones with human faces appearing in, being grouped similar as well. We can do the same thing with music. So what I can do is load up some embedding that I've done with music. So if I load up this TSV file, which contains phrases from a lot of music, I can upload the labels file for that as well. And what I'm going to do is to set the color map by the key of the songs. And so each of those color represents a different key, and the label is going to be the phrase. So now you can see that this is Skrillex, Fine Day Anthem, the introduction to that track. And again, if we run a UMAP on this, what it's going to do is to group the music into similar sounding music, or music that should mix well together. You can see sometimes music in the same key is being grouped together, but here we're getting these clusters appearing. And if we go over here, we've got Depeche Mode Puppets, we've got Robert Miles, and Depeche Mode, Dreaming of Me. If you go over here to the green section, you can see you've got Ed Sheeran, Depeche Mode, various other ones that are grouped together. Now, sometimes you use this, sometimes you do find good combinations of tracks in these sections because they are appearing similar within this high-dimensional space. So, if you're playing around with vectors, embedding and the embeddings projector is cool stuff to play around with. It's open source as well, so you can download it and customize it. So basically, a vector search is some kind of system where we can basically embed items. Like, for example, we can do text embedding, we can embed this text or vectorize it, and we can put it into a search engine. And then we can find the nearest neighbors, which is going to give us text with a similar sentiment. And I'll demo how that works in Azure AI Search a bit later on, because it's a very useful technology. I've shown with images, we can embed the images and we can find similar looking images, and you can also do this with music. This is what Spotify was doing. This is why they developed the vector search capability. If you use Spotify, it will recommend you tracks. Now, typically, a recommendation engine, that's going to work on if I listen to something and you listen to something, then if I start listening to a new song, it's going to recommend it to you. But if a new band comes along and they drop 20 tracks into Spotify, nobody's going to listen to it. And so they can't really recommend it to anybody because they don't have any kind of idea of who would like this music. So what they wanted to do with the recommendations engine is if a new band drops 20 tracks and this sounds like the Chemical Brothers or this sounds like Depeche Mode, then we'll recommend it to people who listen to the Chemical Brothers or listen to Depeche Mode. And there we can use, because we're getting these nearest neighbours, we can use kind of the way that the music sounds as being able to do recommendations using that technology. I don't think Spotify, they're not using the Annoy technology today, but that was kind of why they developed that technology. So within Azure AI Search, I've got a bunch of indexes that do have embeddings on them. I'm using the basic instance of Azure AI Search. It's costing, I can't remember in pounds, maybe about sort of 20, 30 pounds a month to be able to run this instance. And quite a lot of the indexes, I've got basically text, this AI white papers, I've indexed some white papers there. And all of these items. So you can see the actual document count here. This one here is interesting. It's called Every Noise at Once, and it's a fantastic website written by somebody at Spotify. And I screen scraped this website and downloaded, I think it was 450,000 30-second MP3 samples. And you can see that I've got in that search index about 300,000 embeddings of those tracks. So this took about 3 weeks on my home computer to actually do all of the embeddings, but it still works and it does give good performance. I don't know if any of you use Rekordbox, but I actually put the 450,000 samples into Rekordbox and it basically broke it. It took about a minute to start up and then you just couldn't search for anything. It really slowed down. But Azure AI Search is pretty quick. And I've got image indexes there. I'll be demoing and calling on those a bit later on. Okay, so back to the slides. So with text embedding, what we do is we basically are going to use an embedding model. When you work with OpenAI or when you work with one of these LLM providers, they'll give you these language models that are the text generation or chat completion, text completion models. They'll also give you the text embedding models where you send in a piece of text and you get back a string of floating point numbers. And the idea is that if we take a sentence with a certain sentiment, then it's going to have a similar space in that high-dimensional embedding space. So it shouldn't matter if you use different words to describe the same sentiment. It also shouldn't matter if you use a completely different language. This is in Swedish. It's pretty much saying the same thing as the first sentence. And those have similar areas in the high-dimensional space. Again, if you choose a different sentiment, then that's going to come out in a different location. So you can think if you're doing a keyword search, if you're choosing between doing a keyword search and doing a vector search, in many cases, a vector search is going to be the best option there, because when you search for something, it's not going to use the words that you use, it's going to use what you actually mean in that text that you are going to be searching for. So, to demo text embedding, I used to be a C# programmer for so long, I've switched to Python now. And this is something called a Jupyter Notebook. You'll be very familiar with it if you develop in Python. But what it allows you to do is to run blocks of code, keep the variable state in memory, and then run other blocks of code. And it's really designed as a way of learning. Some data scientists believe that this can also be a production environment, but we don't want to go there. So what I'm doing is I'm connecting to Azure OpenAI, connecting to the text embedding adder, the 002 model. Let's see if I can zoom in on this a bit. And I'm declaring an array of sentences. We've got some of the examples that I used in the slides. Oh, I put it in Yorkshire as well. Grub were pucker and barman were sound. I think that's what you'd say in Bradford, where I'm from. And I've also got some other sentences there. So what we can do is we can use the embedding model to embed those sentences. If it's the same sentence, then the cosine similarity is going to be 1.0. However, if I choose a different sentence, which is that one there, you can see we've got this cosine similarity of 0.919. Now, this doesn't mean 91.9% similar. It's the cosine of the angle between those vectors in high-dimensional space. So it's a number between -1 and 1 that gives you an idea of the similarity between those items there. So if I change to 2, now we're comparing English to is it French, and that's still got 0.919. And then if I go to another language, you can see it's 0.9. So it doesn't matter that we're using a different language. It's still saying that the text is similar. If we go to something that means something different, Oh, I think that's still the same, actually. Can't remember how many I put in the array. Oh, try 8. There we go. When I say embeddings are useful for natural language processing tasks, you can see it drops to 0.71, and then if I compare 8 with 9, now we're both talking about embeddings, and that drops out to 0.910. And this can be used, let's skip back to the slides, doesn't no point because the next demo is keyword versus vector search. And what I've done is I've embedded some documents in Azure AI Search. Let's just find the right instance there. So let's just run this without debugging. And I'm programming using the Python API, but it works same in C#. And what I can do is put in some text and just basically search. Now this has, the index I'm going against is the FAQ AI index, which has, I think it's about 20, 30 questions and answers on AI. So if I say, what is AI as a question, we're going to do a keyword search, and then we're going to do a vector search. Now, you can see in the keyword search, we've got how is AI applied in agriculture as the top response. With a vector search, we've got what is artificial intelligence appearing as the top response. Now, in the keyword search, I didn't type in what is artificial intelligence. If I did, that would have been the top result in the keyword search. I used AI instead of artificial intelligence, but the sentiment is the same. And you can see that the vector is picking up the actual sentiment. So I'm a farmer. How can I use AI? And keyword is coming up with how can AI improve accessibility. The vector is coming out with how is AI applied in agriculture as the top result. If I just press enter, we're going to put in that question in Italian. You can see that the keyword result just doesn't get anything. Vector research still gets how is AI applied in agriculture, even though I was asking the question in a different language. So in many cases, if you're building these LLM solutions or general search solutions, vector search is awesome for finding text. It's not always the best solution. There's a project I worked on where one of our customers had gone to a data science company, and they'd basically built this job search thing where you could, and they were data scientists, they thought vectors should be used for everything. And the idea of the job search was they embedded all of the jobs, and then when you uploaded your CV, it did embedding on your CV and did an actual vector match between your CV and the jobs, and that would find the appropriate job. However, it didn't work very well. It couldn't, we had cases, you know, the use cases like a teacher wants to change jobs. So they upload their CV and they says, you know, I've got 20 years experience of working with kids. I want to work with kids, but I don't want to be a teacher. I'd like another job where I can work with kids. And it would recommend lots and lots of teaching jobs. So the vector search for text isn't always the best option. I wouldn't say it's better than keyword search, it's just different. If you work with databases, it's kind of like saying a non-relational database is better than a relational database. You know, they're different things. You use them in different scenarios. Okay, so what's next? Oh yeah, image embedding, taking an image and getting the actual embedding from that. To understand how this works, it's helpful to know a bit about how a convolutional neural network, or a CNN, works. This is stuff I've been doing for about 6 or 7 years, and this is kind of what we used with the auction house. And it's a neural network that will basically take an image, and you can use them for image classification. That's one of the main tasks. And one of the classic things that you do when you're learning about image classification is you get this handwritten digits data set, and you see if you can train a model to recognize handwritten digits. Now, the networks have a number of different layers, and the early layers at the beginning of the network will do things like edge detection. And then as we go through the network, deeper into the network, we do shape detection and then feature detection. And last, we have a linear layer, which does the actual classification. So this is what it would look like if I trained an image to tell between a dog and a cat. Now, the ones that we use, you know, the CNNs that we use in reality, they have a lot more layers than this. ResNet, for example, we have ResNet 18, which has 18 layers, and you think the most complex one is ResNet 152, that has 152 layers. So if you take one of these models, and what you can do is you replace the classification layer with just an identity layer, which just feeds out this information. then you get the embedded features in that image, because all the model is doing is it's identifying all of the features in the image, and then the final stage of classification is saying, based on these features in the image, is this a cat or is this a dog? And if we do that, then we just get the actual features out. And we can use that to create an index and do a search. So you get all of your images, you put them through image embedding, you stick them into some kind of a vector search. And searching for images, you just take an image, you embed it, and then you do a vector search, and you get back similar looking images that you can display. So you can use any vector search for this. So, and then I've got this running in a Jupyter Notebook. This was really the proof of concept that we built for the auction house, but I can't use their images, so what I'm doing is using the dogs data set. You can download this from a website called Kaggle, and it's got like 12,000 photos of dogs and 12,000 photos of cats. And what I'm doing here is I'm using Python and PyTorch to generate a classification model. And PyTorch is really cool. This is one line of code. I'm using the ResNet 18 model, and I'm using the default weights. Now, the default weights are basically what the model has been trained on to recognize a bunch of different classes. So I don't have to train the model. I can just load the default weights, and then I can use it for evaluation. Now, at the end of the model, we've got the linear layer, which takes in 512 features, and it's got 1,000 outputs. So this model can go up to 1,000 different classes when you're doing a classification. We need to transform our images as they're coming in. So what this is doing is whatever the image size, it's going to convert it to floating points, and it's going to be 224 by 224 pixels in that image to do the classification. And then I iterate through a folder, and for each image in the folder, we feed it through the classification model, and we print out the results. So this is showing what the simplest ResNet model will predict for these photos. So it got that one wrong, English foxhound for beetle, but it got boxer right, German shepherd it got right, Labrador retriever, golden retriever, and various things like that. So it's quite good at being able to make those predictions. So to go a bit more technical, what I can do is something very similar but subtly different. So what I'm doing here is I'm creating ResNet 18 model, but I'm replacing the fully connected layer with an identity layer. So if you go back to the slides, that line of code is basically doing that. So instead of getting out a prediction, what we're going to get out is the features, which is going to be a high dimensional vector. So now if I do this, just doing that with one image, we get 512 vectors coming out like that. So that's basically what the embeddings of that dog look like. And we can search for dog friends in the dog vector database by connecting to Azure AI Search and then displaying the dog. And if I choose, say, dog ID 0 and do that search, you can see that we get dogs that look similar to that particular dog. And if we choose another one just to show that that wasn't a fake, if we choose, say, dog ID, let's go for the German Shepherd's off screen, actually. Which one was that? That was 4. And we run that. You can see there, it's coming back with lots of other dogs that are similar to the German Shepherd. So yeah, we got dog recognition working, and this worked just as well for the actual antiques. What's next? Yeah, I've been through that stuff. Oh yeah, face embedding. So yeah, when we have conferences in Sweden, my company is based in Stockholm in Sweden, where I live. We like to set up a booth, and we like to have something cool on the booth, and it typically uses AI or something. So we've had competitions where it's using emotion detection. You've got to look happy or you've got to look angry, and it gives you a score on how happy or angry you look, and then we give a prize to the happiest and the angriest people based on simulating those expressions. So what I thought, it'd be really good fun to build a Terminator. So the idea was that we go to the conference, we go to the speaker's website, we get all the speaker's photos, we contact the speakers and say, hey, we want to build a Terminator on our booth that will recognize your face and say something funny about you when you walk past the booth. Are you okay with that? And speakers are pretty cool people. Most of them say yes. So the idea is that we use something called FaceNet. I was using Spotify Annoy because I want it running without a network connection. I want it running quickly. And then you should be able to take a photo, search for that photo, and it should be able to identify the actual person. I'll show you the demo of that, because what we are thinking of doing also is using the speaker's bio on the website to generate a humorous reason as to how this speaker could use their technical skills to destroy Skynet and say that this person is a risk. And I don't know if you've seen the Terminator films, but they have this kind of Terminator vision thing. Is this the right project? No, that's the wrong project. This is going to be it. Yeah, so depending on the lighting, it may not work, but it worked when I was testing it at the airport. So let's see if it recognizes me. Can somebody put the light? Oh yeah, it's got me. Yeah, Alan Smith. Oh, it did say. Yeah, Alan, given his Azure wizardry, Skynet detects a threat level of duck beneath your metal desk. Fears he may launch an amusing but deadly barrage of virtual servers to overwhelm its circuits in a parody of a hacker's DDoS attack. And I did a demo when I was doing this at the Cloud Brew conference with some of the other speakers. So that's in demo videos. I think it's this one here. For some reason, VLC player takes forever to load on my machine. Come on. Yeah, so this was, I mean, some of these speakers are speaking at this conference here, but it's not recognized Rick Hepworth yet, but eventually it gets him and he's done networking, so he can crawl under the floors and do cables. And this is kind of how it was, how we'd want it to work at the conference. Martin is here as well. It mentions in his speaker profile that he brews homebrew beer, so it's mentioning that he can get Skynet drunk. So that was fun. And then the EU AI Act came along and said you can't use face recognition in a public place, which would have been, you know, the areas in a conference where we wanted to use it. So that was a bit of wasted effort, really. It's a shame. It would have been a fun demo. It would have been cool to have, but it's a fun demo anyway. And the fun thing was, I was in Malmö in Sweden. I was traveling back to Stockholm on the train. So I went into O'Leary's in Malmö and started on this project. I WhatsApped the few of my friends who were speaking at Cloudberry and says, hey, can I use your face for this face recognition system? So I was on a crowded train programming this face recognition system with my camera lighting up and all of this stuff going on. And people are just looking across at me and thinking, who the hell does he work for? And it was fun. I should have worn the black suit and had the earpiece. It would have been fun. Okay, so that's basically how face recognitions work. So getting on to music and the kind of side project that I was doing with working with beat embedding. I never liked electronic music until I think I was at Glastonbury and it was raining and Daft Punk were playing in a dance tent somewhere. So I went to saw them. I think it was in '97 or something, and they were incredible. And ever since I've liked listening to EDM. These guys, again, popped up on my YouTube feed. They're called DJs from Mars, and their thing is to do what you call mashups, where they will mix lots and lots of different music together. This is where I got to be quick on the silence button, because I think there's some offensive language here. Hopefully sound is on. Yeah, I can stop the phone. So they do like 100 songs in 13 minutes.
Buy it, use it, break it, fix it, trash it, change it, melt, upgrade it.
Put your hands up,
Chart it, point it,
put your hands up,
snap it, work it.
put your hands up for Detroit. I love this city.
Technologic, technologic.
Put your hands up for Detroit. Riverside, motherfucker.
I knew I'd do that. I do that every time. I think I've done that at every conference. Apologies for that. So what they were doing is they're using, I think these are like CDJ 3000s or something. They've got 4 of them. They've got a mixer board in there. And what they're doing is they're just basically putting samples together. They've got samples for the acapellas and samples for the music loops. These things are expensive, probably about £2,500 for a CDJ 3000. They've got the 3000X, which of course has AI in it, which is about £3,000. So it's a lot of kit to be able to do that. Another NDC conference, Dylan Beattie, who's also here this year, he did a session on the art of code. I can't remember which one this was from. It might have been an NDC London. But during his session, he mentioned software called Sonic Pi, which meant that you could write code to be able to generate music from the code. And I just paused the video, and the rest of the day, I was working from home at the time, it was this COVID thing going on. The rest of the day I didn't get that much work done because I was playing around with Sonic Pi and looking at making beats with it. And what I was wondering is, can you do, what the DJs from Mars were doing on, 15 grand's worth of kit? Can you do it by writing code in Sonic Pi? So if I just escape out and go into the Sonic Pi, I've got this pre-prepared script that I can run here.
Buy it, use it, break it, fix it, trash it, change it, melt, upgrade it.
Put your hands up,
Start it, point it,
put your hands up,
snap it, work it.
put your hands up for Detroit, a lovely city.
Technologic, technologic.
Put your hands up for...
So it sort of works. Now, a couple of things that I didn't like about that, because I thought, could you do this as a thing, like write code and do a DJ set? And a couple of things I didn't like about this. The first thing is I'm just stealing their stuff. They put in a lot of energy into putting that mix together, and I'm just kind of taking it and doing my own thing. The other thing, this is just static code. You can't really stand there and just, click run and have this thing just run. It would be the equivalent of a DJ doing a pre-recorded set, which I've heard that some people do. It's generally frowned upon. You kind of want to do everything live, kind of mistakes and all. So I got into how do they actually come up with all of those different beats? How can they kind of find what song will match with another song? And there is software that does this. There's something called Mixed in Key that can help you to search that. There's something called Co-Producer, which uses AI to be able to do that. Also in the Record Box and Serato, that will the DJ software, that will give you kind of recommended tracks. But I wanted to build my own software and use vectors because I like writing code, and I wanted to kind of figure this problem out for myself. So one of the ways, if you've played around with working with sound, one of the ways that you can analyze music is use something called a Fourier transform, and you can convert it into the frequency domain and get something called a MEL spectrogram or a melodic spectrogram. And what this is showing is different frequencies over time as it runs through the track. I very often switch, when I'm working in Audacity, switch from the waveform view to the MEL spec view, because you can see where the bass drums are, you can see when various sections are coming in, and where the various musical notes is in. So what I thought is, well, the MEL spectrogram is just an image. So what I can do is I can use a standard image model. There's tons of those lying around that you can just pick up and play with. And I can just do image classification, see if that works, and then I can do image similarity. And I can find similar looking beats. So the first thing I did, just to, as a proof of concept, was to do the actual music genre classification. So what I'm doing is using PyTorch. I got a video from YouTube with different genres of music, and this is the results of that model. So it did eventually, I think, pick up that this was jazz. I'll turn this down, there's some colourful lyrics in there, but hip-hop there is being classified there. You can see the purple track corresponds to hip-hop. Nothing for rock there, but you can see that's metal. I didn't know much about folk music, so I skipped that there. Soul gets classified as disco. And then EDM gets classified as pop. That's the grey band there. That blues, we're getting a strong classification there for blues. And that kind of, I was kind of astounded by how well that worked, just based on the MEL spectrograms of the images. If you want to try that, there is a data set on Kaggle called the music genres data set. We can download music samples, and it was probably about half a day of programming using PyTorch to actually build that. It seemed to work quite well. So I thought, excellent, I can now find similar sounding beats. So all I've got to do is to take my MP3 collection, stick it into Azure AI Search and just do the same embedding as I was using, and taking that model and just modifying that to be an embeddings model, which is fairly easy to do. And so the first kind of iteration of this presentation, I had this notebook here that I was doing with this similar song search. So what I'm doing is I was taking the first 10 seconds of each song and treating that as the actual sample and doing that for my MP3 collection. I'm old, so they're all ripped from DVDs that I bought. And because it's in Azure AI Search, I can do a search like this, search where the artist is equal to the Prodigy, for example. So if I run that, we get the Prodigy songs there. And I think I was using Voodoo People, which was 7 in the results search. So what I can do is do the embeddings on Voodoo People and then search for Voodoo People in Azure AI Search, or search for songs that sound similar to Voodoo People. If you've not heard Voodoo People, it's and obviously the most similar song is Voodoo People. That's going to have a cosine similarity of 1.0. But then it came out with Disco 2000 by Pulp as being the, see if I can zoom in a bit more, as being the most similar song, and I thought, that can't be right. It doesn't sound like Voodoo People at all. And then we've got Therapy. The Dylans. Pixies. And as you scroll down, there's all these songs that start with heavy guitar. So I thought, well, that's cool. I can find similar sounding music. All I've got to do now is mix them together. And it sounded absolutely terrible. And I'd kind of booked, you know, this is a secret, speakers don't prepare a session and then submit it to a conference. It's the other way around. We submit a session, and then if it gets selected, then we prepare our session. So I'm going off, I think it was NDC Oslo or something, and I said, I got this fantastic session where I'm using you know, embedding to do these DJ mixes, and it was just horrible. I knew when I was running the demo that if I picked a certain Depeche Mode song and then I had to pick number 3 and then number 4 and number 7, it would kind of sound okay. But it wasn't really what I was after. So, as with data science projects, you go back to the drawing board and you think of another way of solving the problem using different techniques. So I started looking at music theory. And this is something that was invented hundreds of years ago, something called the circle of fifths. If you've played musical instruments, you may know this. If you play the piano and you play the scale of C major, that's the white notes going from C up to C. If you play A minor, that's the white notes going from A up to A. So C major uses the same notes as A minor. So they appear kind of on the corresponding section on this circle of fifths. And also C major also uses fairly similar notes to G major and F major. So DJs have adopted this, but now it's called the Camelot wheel. I never have really got into this 12A, 11B, 1B, 1A and stuff for all of these keys. I still use the actual names of the key. But the idea is that if you've got a track which is in G minor, then you can mix it with a track, in G major, you can mix into something in G major or E minor or D major or C major. And that basically helps you to understand how you can do the mixing. So the idea of the way that this can work, if you take songs in the same key like Sweet Dreams and Enjoy the Silence, we can go into Sonic Pi. And I've got a bunch of samples here, so what I can do is just, if I take Sweet Dreams. So traditionally it would have the Annie Lennox vocals on the Eurythmics music. So if I go for that,
Sweet dreams are made of the years is. Who am I to disagree? I travel the world.
But then you can swap the actual audio track out for something that's in the same key. So if we take Enjoy the Silence by Depeche Mode.
Sweet dreams are made of these. Who am I to disagree? I travel the world and the seven seas.
And then if you've got other tracks which are in the same key, you can get like combinations that will kind of sound okay. So if we take Patak by Adapter and then take this with Sweet Dreams. And you can take different sections of that and maybe put Adapter, if you take the riser from Adapter and put that with the chorus of Enjoy the Silence.
All I ever wanted, all I ever needed is here in my arms. Words are very unnecessary, they can only do harm.
You get these kind of combinations that sound okay. And so what I did was took a very different approach. Instead of actually working on the kind of similarity using the MEL spectrogram, I basically started looking at working with something called chromatic embedding. So I think I can display this in this section here. I've got a notebook which is showing music theory. And so what I was doing is using a library called Librosa. And what that can do is if I can select a certain track, if I take Alan Walker, Better Off Alone, and we take a section from that. So if I take... I think it's this one.
This could be a good night.
Yeah, so if I just put in ID1 there, we can do the analysis on that. And what I'm doing is I'm first of all creating the melodic spectrogram, which is this thing here. And then I'm also doing the chromatic analysis. And what this is it's taking the musical notes that we've got here, going up from C up to B. And if I play the track, you can kind of see.
This could be a good night for good times, and you look like a good time. We're dancing to dancing in the moonlight. Now I want you back. Can you make me feel better?
So that's basically, you can see we're actually picking up the notes. And what I did is I embedded those and used those in the embedding search. So it's kind of looking for similar notes that are appearing in the tracks, rather than just using an image based on that, which would be based on the features. And I found that although the similar sounding using the features was good in certain circumstances, you could find heavy guitar if you wanted something that sounded like the Prodigy. This was actually getting these kind of melodic comparisons. So this is the notebook that I was using for that. And the way that I work when I'm generally trying to put something together is I'll just go down and find a particular track like Jax Jones, and I've got a bunch of samples from the song Breathe. It takes a while for the waveforms to load up. I don't know if it's this one. The sound in here isn't too
You're on my mind like a song that
yeah, so if I take 4, and then what this was doing, it was taking the embeddings from that, and then it was doing the mixing with other samples based on how similar it was using the actual tones. So we got Sash Ecuador. So this is the.
you're on my mind like a song that I can't escape.
And then this is Sash.
Love me to my love.
Actually, that's probably not the best.
You're on my mind like a song that I can't escape. I don't know how.
And that's the case of going through all of these, just trying to find combinations that sound good, and then try to put a set together by going from one track to another track to another track and merging stuff. But I built many demos for conferences, and this is something that I pretty much use on not on a daily basis, but whenever I'm trying to mix stuff together, I'll use this, and it's quite useful to be able to do that. So that the process that I've gone through is I took my MP3 collection, I put it into Rekordbox, which is software. It's free to download, and it's DJ software. And the cool thing about Rekordbox is if you take, say, Sweet Dreams by the Eurythmics and you drop it onto the play, it basically separates all the phrases in the songs. It figures out that it's 125.2 BPM, and you can see that you've got the actual beats here for that particular phrase of the song. And it also gives you like the different sections, like the choruses and the verses. Now this data is stored in a MySQL database, but the Rekordbox developers, I don't know why they've done it, but they've encrypted that database. And also the waveforms that we've got that are displayed, they're also really, really hard to actually decipher because they put like XOR filters across all of the bitmaps, and it's a proprietary format, which means that the open source developers have to spend their weekends and evenings decrypting the database and figuring out how to actually display the waveforms. But there's a couple of libraries available on GitHub where you can actually get that data out, and this is what I'm putting into search. It's not really a track that I'm interested in, it's a particular section of the track, and each time you put in a different track, it will give you verses and choruses. Sometimes it gives you risers, so I don't know if it will, gives you the different sections, so I don't know if there's anything, will that do it? Yeah, sometimes if it's more dance music, it will give you the risers, like you can see we've got an up there, which is kind of when the song builds up. So it's interesting to be able to find those different sections with a track and be able to mix things together using that. And then what I do when I've got all of those is I do embeddings on all of those. That takes a long time. I usually leave the PC running for a few days to be able to do that. And I'm embedding based on the actual music. I then split the track into all of the separate MP3s, generate the actual waveforms so I can visualize this. The waveforms tend to give you a good indication of the kind of frequencies that are used in the tracks. If we drop back to the Jupyter Notebook, it tends to use blue for something that's treble, red for something that has a lot of bass, and then green for when it's mid-range. So if you're combining, if you're looking for good combinations, you won't want bass on top of bass. You'll maybe want something like that, where you've got don't know if that sounds good at all, but we're kind of combining the frequencies and not putting too much bass or too much treble. So, as I mentioned, Azure AI Search is used for that. With mixing the phrases, it's important to get the actual beats right. So within Rekordbox, they have this thing called a beat sync. Some people call it cheat sync, but what happens when you click that button is it will align the beats of the two songs together. Friends of mine, when I was a lot younger, they had like the old vinyl DJ set up in their dining room. That was a nightmare. If you've ever tried to beat sync on vinyl and get two tracks to match together, it was really hard to do. Nowadays, it's a lot easier with all of the actual software. So what I needed to do there was to take all of the actual samples and put them to 126 beats per minute, which is kind of what I was using in the stuff I was mixing together. If some things are, say, at 130 BPM, then I needed to do that. I was doing that with, there's a software called Rubberband, which is a command line software, and there you can do pitch shifting and tempo shifting in the actual tracks fairly easily, and there's Python bindings for that, so I was running a batch on that to put everything to the same BPM. And what I was doing in the mixing process, as you saw in the Jupyter Notebooks, it just basically you select a track. It then does Azure AI Search, and then I basically programmatically mix together all of the MP3s, so they're all ready to go when you press the play button. So I've kind of shown how the actual vectors works. The fun thing I really like and enjoy with this project is typically, when you go to school or university, when you're studying, mathematics and music tend to be kind of thought about as being two different things. But there's so much maths in music theory, and so much, especially when you start looking at harmonics and musical analysis, there's a lot of mathematics in there. Also, computer programmer and DJ are kind of two different things, but I really like the way that you have this software like Sonic Pi and Strudel, where you can actually write code to be able to put on DJ sets, which has become quite popular. Mixing genres together. I had one section in this mix I've put together that is using all of these different tracks that are in many, many different genres. So it uses mixing Pink Floyd with Orbital and with Opus 2 and Dimitri Vegas and Skrillex. I can show you, I think I've got a few minutes so I can kind of show you what that sounds like. So we're using, if I drop on Time by Pink Floyd, that's the introduction to Time. And then if we take It's a Fine Day, Opus 3. I think it's going to be number 3 on there, and that needs to start at 0.5. And then I can take track 4 from that. So there's an offset of 32 beats in those two samples, so that's why I need to do that. And I can sleep for 32 beats. I need to be running at 126 BPM, so I'll set that up there. And also we can drop on Orbital. So that's going to be the bass line from Halcyon and On. And if we stick another mix of that, that will be 64 beats. And then we can bring in Dimitri Vegas and Skrillex. And see what that sounds like. Too much bass on the sound system. I don't know if that can be fixed.
They walk by the grass. They look at the sky. They walk by the grass and they look at the grass. They look at the sky.
So I kind of like that combination, be able to mix different genres of music together. So if you're interested in this, I've got some slides on that coding with music that I can talk about a bit later on after the challenges. So challenges in the project, one of them was hard drive space. There was just so many MP3 files and the embedding files and all of the images and different mixes. I was actually running Performance Monitor on my F drive as I was actually running all of the actual processing, because I kept running out of hard drive space. I actually bought another 4 terabyte drive just for the actual music stuff and then the data sets I was using within this project. It was getting ridiculous. That was partway through the project. I've got over 1 million files now, and it's over 1 terabyte of stuff that I've got relating to that particular data set. Another one from Dylan Beattie was just dealing with all of the weird characters that some of the artists have in their songs. Another of his presentations I always used to show on my integration courses was there's no such thing as plain text. These things as well. Does anybody know what these are? When you're working in Visual Studio, they look exactly the same, but there's a hyphen, a minus sign, a non-breaking hyphen, an N dash and an M dash. They're all different characters, and when I was splitting and getting the artist and the track name out, that was causing problems. And then, you know, when I was young, we had songs like Park Life by Blur and Oasis Wonderwall, and these days you got tracks and names and artists like that, which isn't fun to deal with when you're trying to get stuff to fit on the user interface. More research. Some great data sets. I haven't had a chance to look at this, but this is a Chordonomicon. 666,000 chord progressions from different songs. So I bet there's a ton of stuff in there that can be used to analyze and find more stuff that can be mixed with. Also, some great white papers. People have looked at things like detecting drops in EDM using different approaches to be able to analyze the music. And I did have some video. I was looking at actually analyzing sets and looking at what was going on in a set. So this again is a DJs from Mars set, and what I'm doing is using the Python library to be able to actually figure out RMS, centroid and onset, which is looking at the energy changes in a mix. You can see that band there is the mel spec, and then below that you've got the actual dominant note that's appearing in the track, which is coming here if I just full screen it like that. And these graphs are basically showing what's happening in the set with relation to the actual energy levels when they're getting the build-ups and when they're getting the drops. You can see here there's a change with that red line. And looking at how and what goes on in the DJ set with all of those levels there, I've got, I think I've got 1,200 Tomorrowland sets, and the Essential Mix on Radio 1, I've downloaded all of those as well. That's available on the Internet Archive. So that's going to take a few weeks to trawl through and do the analysis. Did you have a question? Oh, okay. Yeah, thanks. And then, yeah, if you want to get into the music from code, I've got a couple of minutes left. I'm using something called Sonic Pi. There is also something called Strudel. And DJ Dave, real name is Sarah Davis. This is using Strudel to create dance music.
Is what it sounds like with a 4 on the floor. So I have this arpeggiator that's running through a sequence of notes or chords, and it's using a supersaw sound. And I have the envelope set here, and also a low-pass filter envelope that's on a slider. So if I change the slider, it's going to make it sound brighter. And then I have a similar setup on this bass line up here, where I have the low-pass filter slider set pretty low, so it sounds more like a bass, but it's using the same sound, and it's running through just a different sequence of notes. And then on both of them, you can see I have post gain set to a variable. So that variable basically makes it possible for me to sidechain these sounds to a kick drum. So if I bring those patterns in, it's also going to bring the kick drum in. And here is what it sounds like with a 4.
So that's just showing what she can do with Strudel. So just a few resources if you do want to take a look at that. If you want to create music with code, I'm using Sonic Pi, but Strudel you can also download. I think Strudel gives you more control. It's better if you're working with like soft synths because it allows you to do things like side chaining and mixing and put these sliders on the actual code. I think that's JavaScript based. Sonic Pi is based on Ruby. And then check out Sarah Davis as well on YouTube there. This was from like an hour-long set that she did. So she's been playing sets at conferences. Tomorrow at the party, I'm hopefully going to do a live mix with the stuff that I've been creating in here, just for about half an hour, 45 minutes. So if you just do want to drop into that. I will be around tomorrow as well for questions, most of the time probably in the afternoon. So feel free to drop in if you've got any questions. Thanks very much for listening and enjoy the rest of NDC London.